Hello everybody. So today we will continue the discussion for engine design. Okay, as you know, engine design here we are talking about internal combustion engine. So this is the layout of internal combustion engine. It consists of the valve, exhaust valve, cylinder head, cooling water jacket, the piston, the crankcase, the cylinder block, the intake valve, and the camshaft. All right. So what happens in the engine is that the air and fuel mixture is fed and it is compressed and then it is light, and this causes the energy release from the combustion, which is used to move the piston down, okay, and generates the amount of pressure and causes the engine to rotate in the second cycle, and this is repeated for every cycle. So to harness the engine power, we have to take a connection from the piston to the crankshaft in this case. So the piston will transfer the load from the gas combustion. It will deliver to the piston pins, and the piston pins will connect to the connecting rods, which will be connected to the general bearings of the crankshaft. So the piston is moving in a linear motion, but however the linear motion is turned to a rotary motion through the crankshaft design. So in this case, the design of the crankshaft causes the power and torque to be transferred from the combustion engine. So this movement will create a reciprocating motion of the piston so that the power are transferred. So firstly, in terms of history, I think you all done this before. Otto cycle is created by Nicholas von Otto, and he himself created these engines. Okay, and later Daimler also developed the engine to run petrol, and Rudolf von Diesel also created a diesel engine. So the common movement of an engine is there is an intake or induction stroke, uh, and here the piston goes from the TDC or top dead center. The intake valves are open and the intake valve closes when the piston reaches slightly below BDC. Okay, and then there is a compression stroke which begins as the piston starts to move from BDC to TDC again, and which after that combustion occurs and the fuel is burned. So this is the two strokes for induction and compression if you look at the picture A and B. And after that there is a power stroke where the fuel and air is ignited. For petrol engines there is a spark plug. For diesel engine it is just auto ignition. Okay, so the highest cylinder pressure occurs during the combustion, okay, and which moves the piston down. And if you look at C, the pressure, there is a big pressure rise in the diagram for at TDC, at the combustion chamber, which causes the power to be pushed down until the piston is moving back to TDC. And after that, the exhaust stroke, where you have to deliver or remove all the exhaust gases that has already been combusted. So this is the general PV diagram of a combustion engine. Theoretical is on the left hand side and actual is on the right hand side. You can see the actual PV diagram is not squarish, it is filleted at the edges. So the engine firing order states the sequence. So when you talk about engines, motorcycles engines are single engine, so you can talk about the easily the strokes. But when you talk about multi-cylinder engine, there needs to be a firing order. So the firing order makes sure that each power stroke is delivered at the correct angle of the crankshaft. So if you look at here, normal engine, four-cylinder engine, multi-cylinder engine, it is 1342. So if you have a V6, it is 145,236, and so on. Okay, so they have to be like this so that the stability of the engine is not compromised. So engine rotation, okay, to meet the SAE standards, nearly all the engines rotate in a counterclockwise directions. Okay, so this is important because later on when people want to design the flywheels and the gear mechanism, they have to use the counterclockwise direction to make their design. Okay, this is Rudolf van Diesel. So he created the diesel engine. Right? So diesel engines are similar to petrol engine, only that there is no spark plug. Okay, the fuel is compressed to a very high compression ratio. Then the sparking occurs, but generally it is similar to the gasoline engine. Right? So this is the PV diagram, and this is the theoretical PV diagram for the Otto cycle. So you have 6 to 1 is constant pressure induction, 1 to 2 isentropic compression, 2 to 3 constant volume heat input, 3 to 4 isentropic expansion, 4 to 1 volume heat rejection, and 5 to 6 exhaust pressure gas is released. So this is the thermal efficiency of a Otto cycle. So efficiency equals to 1 minus 1 over compression ratio to the power of K minus 1. So normally for SI engines, the thermal efficiency is between 7 and 10. Okay, and maximum you can get is around, if you look at the compression ratios, okay, generally a car is around 40, or in this case they're showing 60, but I don't think it will go to 60. So when you talk about engine performance, you need to calculate the engine displacement. So engine displacement is calculated by this, where the displacement is a volume of the cylinder that includes the combustion chamber and the stroke of the engine. So this is one cylinder plus with the combustion chamber. So typically engine performance parameters is you have to find the torque, the power, the fuel consumption, and the emissions. How? You normally use a dynamometer, and the engine is hooked to the dynamometer. Okay, as the engine is moving counterclockwise, the load at the strain gauge is given a force, and this arm will create a torque movement. So rotational speed of the dynamometer is measured by using the toothed wheel and the pulse center. Okay, so the RPM is determined from the engine, and with these two, force and motion, you can calculate what is the kinematics of the engine. So the flywheel connects the kinematic energy. So this energy is in terms of half mr squared. The m is the mass and r is the radius of the flywheel mass. So this is later on we will do at the end of the semester. So when the engine has the maximum pressure at the combustion, the peak pressure will rise at TDC but rapidly drop as the piston moves back to the PGC. So the mean effective pressure is the highest pressure that can occur on the engine. So this pressure causes tremendous effect to the materials of the piston. So this is your point of contact. So we need to find a way to calculate this. Okay, and tomorrow I will try to give you a software which you can use to calculate the piston mean effective pressure. So from this pressure we can use to calculate the material design that we are going to make for the piston. Okay, so the torque is again from the dynamometer. The torque is given by F times the R. Okay, F is the force applied to the crankshaft, and R is the crank arm radius. So engine performance is also deeply dependent on the displacement and the compression ratio. So normally typical engine will have a volumetric efficiency of 0.8 and thermal efficiency of around 30% and mechanical efficiency around 25%. So normally the overall engine is only about 25% efficient. So for the assignment 2, so you need to calculate the power and torque of the engine that you selected, okay, and the BSFC if possible, okay, but I think maybe we need to calculate the power and torque only. All right, so later I'll give you Google forms for you to fill up and calculate these parameters based on your dimensions that we did last week. Okay guys, thank you very much.